Well, this is fifth lecture in the series of Mechanics of Metal Forming E-content course. Last time we discussed the stress strain and then how load displacement curve is drawn using a tensile test. This tensile test further used to draw the stress strain curve for any material. The stress strain curve is used to give so many information about the material properties that is later utilized for different processes in metalworking. This lecture we will discuss the flow curves as last discussed, then the flow stress and average flow stress, then what is the effect of strain rate and what is the effect of temperature, and how do these control different material forming processes. So basically one can see this video which shows the working of a machine tensile test. It's a short video. This video says that how the workpiece is loaded, how the deformation takes place, and after deformation the workpiece is taken out and slightly reworked, and that's how one can visualize the actual working of tensile testing. Before starting, let us see what is plane stress and plane strain, because this part is important as far as the modeling of metal forming processes are concerned. The plane stress is a state of stress in which one or more of the pairs of faces of an element, like the cube element last time we discussed. Generally the cube are free of any stresses, that is the torsion of thin wall tube, expansion of a thin wall, spherical cell under internal pressure. These problems are solved under plane stress condition. One can see here on the left side of the figures, the three figures, the plane stress says that in the z direction the stress is 0, while the xy direction, that is sigma 1 and sigma 2, stresses are there. So one can analyze problem based on plane stress. On the other hand, the plane strain, where the state of stress where one of the pair of the faces of an element undergoes, that there is a zero strain. For an example, the torsion of thin wall tube, piece of material being compressed in a die, all these examples can be solved using plane strain conditions. Certainly the plane strain means z strain is 0 here, but the stresses would be present. So this simple classification helps to analyze different natural problems concerning metal forming in a way when you simplify the problem either by plane stress or plane strain analysis. Let us see, remember last time lecture, the true stress and true strain curve, if you plot it on log-log plot. So what will happen? The true stress, one can see this equation where it can be equal to A and then the true strain raised to the power n, and then you take the log of this. So you can plot it log true stress on the y-axis and log true strain on the other, and you get a straight line. So it's a beauty of log plot of the true stress. It gives a for an example, this particular curve is shown and that becomes a power law. It's a straight line. So this power law is a representation of the plastic stress strain curve relation for copper. So similarly, likewise, you can convert any stress strain curve on using the true stress and strain on log plot, and that gives a power law. Let us see. We also speak, and it is very popular to define incremental strain, because when we talk of the stresses in forming, the things continues, that you have to continuously apply the stresses in the strain in the incremental form, and there is associated energy required. So for each associated incremental strain, one can see here delta x. If the delta x is the increment, so from the stress strain curve you can find out the energy required, and this energy gives an idea for the process to continue how much force energy is required. On the other hand, right hand side, the total energy one can calculate based on this incremental strain dissipated till the maximum limit, that is the ultimate strain, because after that the material is bound to fail. So it has been considered only up to maximum limit. There are different materials where data are available, like the ancient iron, which has the maximum strain, it is around 0.03%, whereas for maximum stress for the ancient iron is around 70 megapascal. Modulus of toughness one can calculate in megajoule per meter cube as 0.1. Density of the ancient iron is well known, it is 7,800 kg per meter cube, and the maximum energy that for the ancient iron is, it comes up to 1.3 joule per kg. Likewise, for modern spring screen, like the maximum strain 0.3, maximum stress is supposed to have 700 megapascal, modulus of toughness is 1.0, density is around same as 7,800, and however the maximum energy goes to 130. Now you see the energy absorbed, and then if you see the your wood, it is 0.3, 120, 0.5, 600 and 900. So now you see the wood, it's not wood, it's a material, it's a metallic alloy, like tandem for the maximum strain where 8.0, maximum stress is 70, and modulus of toughness is around 2.8, density comes to be 1100, but the energy is around 2500. Whereas if you see the rubber, which is a your wood is a kind of wood, sorry, the rubber on the other hand, there are different classes of rubber that absorbs different level of energy. So usually the maximum strain that can be taken by a rubber material 300, and the stress corresponding is very less as 7. Modulus of toughness is 10, density is around 1200, and the maximum energy that it can absorb is 8000 joule. So this shows that the incremental strain is important, as the different material will have different energy level for strains. If you look at the stress strain relationship, in the plastic deformation region called bag is described by this relationship can be very well described by sigma is equal to strain raised to power n, and this equation is well known called as flow curve, where capital K is the strength coefficient in megapascal and epsilon is the true strain, the sigma is the true stress, and n is the exponent which is called as the strain hardening coefficient. Generally the value of n is 0 for perfectly plastic solids, is equal to 1 for perfectly elastic solids, and it ranges from 0.1 to 0.5 for most of the metals. The flow stress, if you now say corresponding to this particular flow curve, flow stress, and let it is denoted as YF, then it can be used for which comes into the beyond the yield. When yielding starts, after that this flow curve can be fitted to corresponding flow stress for different materials. Let us see on this figure the flow stress as the deformation occurs. Increasing the stress, it is always required to continue a particular deformation process as shown in this figure. One can see here after the upper yield point, one has always to, once it reduces after the lower yield point, there is always increment of the stress to be done so that the process continues, and therefore there is an instantaneous value of the stress which is required to continue deforming the material, and that is how one can say keep the process to flow, and therefore this flow stress is given in this manner. One can see here that the hardening region and the softening region. Hardening region because of the strain hardening, and there is a great role of the flow stress for different materials. Then there is again a concept of average flow stress, where there is you can average the whole curve of the flow curve. So for many bulk deforming processes, rather than instantaneous stress, average stress is generally used, like extrusion process. The average flow stress can be obtained by integrating the flow stress along the trajectory of the straining from 0 to a given final strain value, which is defined in the range of the interest the figure as shows. So the average stress can be written as the bar YF, which is equal to the K epsilon raised to power n, and the denominator side is 1 plus n, where n is the strain hardening exponent, K is your strength coefficient, and the epsilon, or this is the maximum strain during the deformation that comes into. So this flow stress is very popular for simplified manner to find out the minimum stress required to have a strain increment to continue. You know, this flow will occur generally any forming process happens with a particular speed. If the productivity is concerned, the speed of the forming has to be increased, and so concerned with strain rate, how quickly you want, how productivity you increase, it is directly with the strain rate, and therefore the evaluation of strain rate is also necessary in all metal forming processes. Generally it is defined as the strain dot, so that is strain rate, which is the ratio of velocity and the change in height h. In most practical operations, evaluation of strain rate is very complicated, generally because of the work part geometry, and secondly because of the variation in strain rate in different regions of the part. And the strain rate generally can reach of the order of 1000 per second or more for some of the metal forming operations. So that's how one can see there is a great importance of strain rate in metal forming. The strain rate is so dependent on temperature. It has been observed that when you strain at higher speed, the material itself because the dissipated energy becomes more and conversion of the energy in the. However, this happens at the cold condition. But if you increase the temperature, because the softening of material takes place and the yield point reduces, and therefore the strain rate one can have a higher, and so therefore there is a role of temperature, that is elevated temperature on the strain rate. So strain rate at which the metal is strained in a forming process is concerned with temperature as well. In the hot forming or warm forming, the strain rate can affect the flow stress therefore. Like if you see here, the strain rate then can be, this is a case where the extrusion, there is a ram which is applying a force F, and there is a die and workpiece material, that is billet inside. Initially the billet length has been H, and after extrusion through the die, the product comes out at speed V. So one can define the strain rate for this particular case, where the speed of the forming is V, ram force applied is F, and H is the length of the billet. So the speed of deformation can be said as the V, and therefore the strain rate can be evaluated as V by H, where H is your instantaneous height of the workpiece being deformed. Initially it can be a billet length, but as the extrusion continues, the stroke of the ram continues, this goes on reducing, and therefore it is said that H is an instantaneous height. Then you can now calculate the flow stress, and this becomes capital C, strain rate raised to the power n. So now you see this particular equation, the previous equation was not having strain rate, but if you incorporate in strain rate, this becomes capital C, strain rate raised to the power m. So C is your coefficient, strength coefficient, but it is not as same as K, and m is your strain rate sensitivity exponent, which depends on speed of the strain rate. So now you can see the difference between the strain rate, the equation of the flow stress, and simply there is no strain rate, then the flow stress are different. The equation seems to be almost same, but the value of C and C is different. So C and M are determined by the following figure, which generated from the experiment as explained earlier. Like you see this figure, where one can find out if it is a non-linear flow of the at a particular strain rate, for an example 1, 2, 3, the flow stress can be determined, and this gives the intersection at flow stress, that is the y axis, gives the C across at a particular strain rate. And similarly, if it is a linear flow material, then same thing can happen like this, and the slope of this at a particular point will give the value of m, that is the strain rate exponent. So you can calculate value of C and m from corresponding to a particular strain rate. Now if you have, and this happens with a particular given temperature, there is a temperature rise like this figure, so the value of C and m are affected by temperature. One can see here the effect of temperature on flow stress on the left side of the curve for a typical metal. The constant C here indicated by the intersection of each plot with the vertical dashed line at strain rate 1, let us see. So it decreases as and m, which is the slope of the plot, increases with the increasing temperature. One can see here, as the temperature increases, the value of so you can calculate from the flow stress that C is strain rate to the power m. So at a particular temperature you can find out of the given flow curve the value of C and m, and then one can see increasing the temperature, the value of m and C, you can notice it decreases. Increasing temperature, you can see it decreases C and increases m. If you increase the temperature, there is a decrease in C and increase in m. Usually at room temperature the effect of strain rate is almost negligible, and therefore the flow curve is a good representation of material behavior, and as temperature increases, strain rate becomes increasingly important for determining the flow stress. So the role of strain rate and temperature is combined is very important in all kind of metal forming processes, and especially bulk metal forming processes. Even in cold work, the strain rate could affect the flow stress. This we have already seen. A more general form of the flow stress with consideration of the strain rate and strain can also be given like here, where the flow stress is given as capital A, then strain raised to the power n, and strain rate raised to the power m, where A is the strain coefficient, a combination effect of which is equivalent to the combination effect of K and C. All these coefficients, that is capital A, n and m in this equation, are function of temperature. So there are separate equations for A, n and m. Usually the tensile tests are also carried out for high temperature materials, elevated temperatures. So elevated temperature as affects the properties of metals. These effects may be determined by carrying out tests like the tensile test at various temperature while keeping the specimen inside a given furnace. In other instances, upset for forging of test workpiece is carried out. Therefore, these kind of tests deal with short time plastic behavior of the materials. If longer the time are considered, the phenomenon of the creep is significant, and materials yield at elevated temperature very slowly under stresses which are considerably lower than those needed for a fast plastic deformation. So these considerations are very popular in metal forming. One tries to draw different curves at different temperature, at different strain rate, and at particularly elevated temperature to get the overall characteristic of a particular material. Here is the structural steel curve, experimental stress strain plot for 1018 steel. One can see here it's again the yield point. One can see here the upper yield point and lower yield point is almost very close, and there is a fluctuation. So you see that it is very stiff, the curve is very stiff, and so the different steels, as the alloys are designed, one can expect different curve of this nature. As far as the characteristic stress strain curve for a brittle material is concerned, for an example cast iron, one can find this here, because the cast iron there is no yielding and it breaks, and therefore one gets the stress strain curve like here, where it is for the ductile material is here, like the aluminium one can see here, and this is for cast iron, the compression test. See, like we do tensile test, one can also perform compression test. So this is for cast iron. You see that there is a difference between the tensile test and compression test. For the same material, the curve is below compression, the load, as far as the compression requires more load as compared to the tensile workpiece. Similar happens in the copper for the compression test. Here the nature is almost similar as the tensile test. One can also calculate the Young's modulus. One can also calculate the proportional limit, yield strength, like this way, using a given stress strain curve. So one can find it out here. One can also find out the proof stress and all that. One can find out resilience, which is the modulus of resilience under the curve up to elastic limit, and toughness under the curve at the fracture limit. So amount of the energy absorbed by a material up to a fracture point. So these are all important, and one can derive from a given stress strain curve. One can calculate tangent modulus at a particular point. So the slope, the tangent modulus is slope of a line tangent to the stress strain curve at the point of interest, like point A here. It is used to describe the stiffness of a material in the plastic range. So from A onward you can find out at any. There is a second modulus also, which is again a slope of a line from the origin of the stress strain diagram and intersecting the curve at a point of the interest, like A here. It is also used to describe the stiffness of a material in the plastic region, like this curve. So these are all derived one. Another interesting thing is a Poisson ratio. Poisson ratio you cannot get from the stress strain curve. So you have to derive it, and the Poisson ratio can be determined indirectly from the stress strain curve by knowing the change in the cross-sectional area of a specimen at a point along the elastic region of the stress strain curve. Like here, one can, the original geometry is given as this, and once it is deformed, that is, it is compressed, so one can find out the stress because of, so there is a change, the initial with B is changed to B plus delta B, and the height also reduces delta A. So one can calculate the Poisson ratio as lateral strain by axial strain. Mostly the Poisson ratio for metals varies from 0.3 to 0.35. For ceramics it is 0.2 to 0.25, and for most polymers the value of a Poisson ratio falls between 0.25 to 0.5. There are some interesting points that are associated with Poisson's ratio, that as I told, for the metals it falls between 0.25 to 0.35. For rubber it is almost close to 0.5 and is therefore almost incompressible. Cork, if you see, the Poisson ratio is close to 0. This makes the cork function well as bottle stopper, since an axially loaded cork will not swell laterally to resist bottle insertion. The Poisson ratio is bounded by two theoretical limits, that is, it should be greater than -1 and it should be less than or equal to 0.5. That's the important. So it is rare to encounter engineering material with negative. It is very rare that we fall the engineering material the value which is -1. It is very rare. Generally, when we in forming, we deform material up to the limit where the failure do not take place. So there are failure theories, and limit this failure theory decides what should be the limit of forming, and therefore it is of importance for designing a forming process. Basically, if we see, there are two classes of material, isotropic material and anisotropic material. Especially for the isotropic material, only two independent constants are needed for describing the stress-strain relationship, like the Hooke's law we have seen, where the stress divided by strain is the Young's modulus. Two, for the failure theories, as for the ductile material, we consider the maximum shear stress criteria and like von Mises criteria. And for brittle material, we consider maximum normal stress criteria like Morse theory. These two criteria, when we discuss the chapter of yield criteria and theory, we would discuss in detail there. However, there are non-stress based criteria also, which is used in stiffness, vibration, characteristics, and fatigue resistance, creep resistance, etc. We will discuss one by one in due course of the time when it appears during the lecture. It is also very important to know the hardness of a particular material, because that is also a property. For the hardness, usually a resistance to plastic deformation by indentation. So there are different tests are carried out again on using different machines, like the tests like Brinell hardness test, Vickers hardness test, the Knoop test, then Rockwell test, and Rockwell tests at A, C, D, different scale, B, F, G, E. So for different scales of the Rockwell, we use different types of indentation, like diamond cone, like steel balls, of different diameters. This table shows the shape of the indentation and the corresponding hardness number. So hardness number, one can see it is directly dependent on the size of the indentation, and the type of the indentation is also shown here. So one can derive it after. So this property hardness is it also adds. Likewise, the shear stress and strain for the torsion test is this popular equation where you calculate it, and there is a term called as modulus of rigidity. It is also popular for determining material properties. Likewise, the shear stress and tensile stresses are calculated for different tensile strength materials. One can find out that the tensile relationship and the yield relationship, these are very popular one, and it is also part of material property. Fatigue strength is also calculated, for which is the fracture failure of a material subject to cyclic stress. This is also important, and therefore SN curve is very popular for compressible loading under, and we find out then there are failure under impacts, like it was discussed, like the drop form of forging, tensile for the impact, testing for the impact strength, like you do the Charpy test. Then the strain hardening, where you also look into the metals microstructure, crystal grains under plastic grain slipping along boundaries. You look up to the grains which is increasing for increasing the strength. We see this in the true stress strain curve also you can identify, defend. Generally these applications of strain hardening happens in cold rolling, forging, part, because the part becomes stronger as it is than casting when there is a strain hardening and all that. There are residual stresses which are internal stresses that remains in material after the processing is done. So, and that causes the forging, drying, where the removal of external forces. In casting also there is a variation rate of solidification, thermal contraction and all that. This all happens because of the residual stresses if it remains, and therefore there are problems like warping when the machining is done, creep and all that. One can see here that before a particular if there is residual stresses, then it will make tear. The residual stresses may tear. There are many cases like A, B and C here, where releasing the residual stress is helpful, and that process is called as annealing. There are properties, physical properties, like as we have seen, and for density, specific heat, apart from the we get from the tensile test, the melting point, coefficient of thermal expansion, electrical conductivity, magnetic, these are also concerned, but we cannot get it from the tensile test. When we conduct forming process, there is a great role of friction, like all forming processes, because the material is flowing and it gets retarded because of the friction, and therefore the forces and powers are increased to overcome the friction, and also the wearing of the tool is faster. So the friction and tool wear are more, so we concern the friction as well, and therefore the lubrication of the metal forming it becomes necessary, where you require a lubricant onto the two workpiece interface in the processes to reduce the harmful effect of the friction. This putting the lubrication, it gives benefit like reducing the sticking of the metal, reducing forces, reducing power, reduction in the tool wear, better surface, and it also removes heat from the tooling. So lubricants are very popular. Generally popular lubricants, it depends on the process, like rolling, forging, sheet form. For our hot working or cold working, what is the work type material, the chemical reaction with the tool and the work metal, and what is the ease of application and what is the cost of that. So based on all these 6 points, one can choose a particular lubricant, and therefore this talk, all the proceeding, you can test yourself on the objective questions, and I thank you for this. And but please do not forget to give your feedback so that we can improve upon. Thank you all.